Hello everyone, welcome to Elec-04-Transformer and heat equivalence. So when you talk about transformer, you might think of this little robot thingy. This is not what we're talking about today. A transformer is a passive component that transfers electrical energy from one electrical circuit to another, or maybe multiple circuits. So usually when the electricity is transferred into your household, you need the transformer looking something like this to convert the energy from high voltage to lower voltage for more efficient use and maybe efficient transfer. So inside a transformer, it looks like this. So you wrap the wire of the incoming wire called the primary winding. So this primary winding create the magnetic flux, and as you know that we're using alternating current, so the alternating current would generate magnetic flux that are switching back and forth. So this magnetic flux would induce the flux on the other side, creating the current flowing on the secondary winding. So this secondary winding is going to give you the power that you get to use on the output. So this is the incoming, this is the outgoing, and the number of winding is going to determine how much EMF you're going to get. So to calculate the electromotive force or the EMF, you can actually use this relation. So let's say you have the electricity coming in, the primary winding being N1 and the secondary winding being N2. So the flux would be induced like this, or alternatively you can have N1 right here and N2 right here, so the flux would shake around like that. So regardless, the ratio between the number of winding N1 versus N2 is going to give you the ratio between the total EMF. So E1 divided by E2 is going to be N1 divided by N2. So the more winding is going to give you the more EMF. So this ratio is going to tell you how much EMF you're going to get in the final readout. So if N1 is more than N2, then E2 is going to be less than E1. So this is a step down transformer. And if N1 is less than N2, E2 is going to be higher than E1. So that means that this is going to be a step up transformer. So a step down transformer convert higher EMF to lower one, and step up transformer convert lower EMF to a higher one. Regardless, this is done with the conservation of energy. So therefore, with the lower voltage, you're gonna get higher current, or lower, or higher, or lower voltage. Yeah, sorry, or lower voltage, and then you get higher current. So regardless, you're gonna get the same output energy. So another tools that you're gonna need to learn how to use is the kilowatt hour meter. So why kilowatt hour meter? So when you're reading things like this, you would probably heard of the electrical energy in terms of the units. So for each household, you're gonna have this kind of winding going on. So this winding is actually gonna be given as the reading where the energy is being flown into it. So this right here is gonna keep rotating, and then as it rotates, this number is gonna go up, and once the number goes up to the point where the number on the black box goes up, this is 1 kilowatt hour. So if you calculate 1 kilowatt hour, then you can actually multiply 1000 for a kilo with the hour into the second. So a watt is joule per second. So this is 1000 joule per second, and then the hour is going to be 3600 seconds. So multiply these two, and you're going to get 3.6 times 10 to the 6 joules. So this is a lot of energy. So therefore, when you use the electrical energy of one unit, then you need to read this into conversion. So this is just 1 unit of energy. All right. So again, the disk is going to keep rotating, as you noticed earlier. The disk rotate, but the number never goes up. So it means that the rotation needs to rotate several rounds here. So for example, this one says 1200 round per kilowatts hour. So that means the big N is the number of turns until the number of the unit go up by 1. So 1200 is going to be your big N, your capitalized N here. So if you watch this rotation and it rotates for N rotation, then you would have the electrical energy being spent just by counting the number of rounds here. So you just count the number of rotation of this and divide it by 1200 here, and then multiply that by 3.6 times 10 to the 6, then you get the joules. So as you count the time, if you want to calculate the power, you know that if you know how fast this thing rotates, so you can just count the number of rotation per time. So if you let it rotate for times t in seconds, then you can actually calculate the power in 3.6 times 10 to the 6 times n divided by capitalized nt, and that's gonna come out in watts. So just by counting how fast the disk rotate over time, you can actually calculate the power, or you can calculate the total energy being spent here using the kilowatt hour meter. All right, so our setup is gonna be you're gonna ultimately be using the electrical energy coming from the outside, then going through a transformer, and then you measure the current, then you measure the voltage, and as you know, current times voltage is gonna give you the power. So you can actually read the power from this thing, and then you're gonna use this as a heating coil to heat the water inside of the calorimeter as you stir it, and then measure the temperature. So, all right. So, part one. First of all, you're gonna be doing some calculation. So, you're gonna be plugging in the light bulb with determine wattage, and then you turn the whole thing on, and then you read how much power is being drained. And in the meanwhile, you could also be doing the same calculation by you know. So as I mentioned earlier, you can count the number of rotation here to calculate the power if you know how much this thing rotates over time. So that's gonna give you power in watts. The other thing that you can do is measure the current directly and measure the voltage directly. And this one is a little bit dangerous. So be sure to set this to AC voltage of 250. As you know that the voltage in our household is 220 watts, so the voltage is pretty high. So be careful with this. So you get 220 watts here, and then you read the AC current here. So multiply these two, you should get P equals IV for the wattage. And alternatively, you can count the number of rotation over time here, and then measure what is the wattage here, and you can read the wattage on the bulb itself, and compare these three numbers in part one. Part two, you're going to be playing around with transformer. So this is a small transformer. So the electricity comes in through this wire, and then this is going to be your primary winding, and this is going to be your secondary winding. So the secondary winding is you need to wind this yourself to make it like 7 round, 8 round, 12 round, depending on what it says in the manual. And this right here is going to be 700 rounds. So this is going to be a step down transformer. So N1 is 700 and N2 is whatever it says in the manual. And from there, you're going to be reading how the transformer works by wrapping this wire around here, and then rewrap it again on the side. So by wrapping on the side, you would notice that the magnetic flux is going to be half, because magnetic flux comes out and then is split into two halves. So if you wrap at the center, you get the full magnetic flux, but if you wrap it in the side, you get half the magnetic flux. So by getting half the magnetic flux, you should get half the reading as well. So be sure to compare that with the calculation of the EMF equation based on the number of rounds. All right. So on the last part, you're gonna be using a step down transformer, and then use that winding to create the current goes into the water heater inside of a calorimeter, as I mentioned earlier in the diagram. And from there, you can actually measure the power and measure the heat that goes in, and then you can measure the thermal energy by using a thermometer. So technically what you need to do is you need to make a calculation. So based on this thing, you get the electrical energy in, and then you get the thermal energy out. So then right here is the time it takes before you turn on the heater. So once you turn on the heater, the temperature is gonna slowly goes up. But as you know from previous lab, that this thing is gonna cool down by itself as well. So you're gonna need to be turning this thing on from point B to point C, and then from there, after you stop, it's gonna cool down a little bit. So what you need to do is to make the same correction to find the final temperature, to correct for the thermal energy loss by dragging a dotted line here, and then draw this center line to make the area from the left hand side and the right hand side to be the same. Then make this interpolation to find the final temperature. So the thermal energy differences is going to be the mass of the water times C equals 1, and the mass of a calorimeter, and the mass of the stirrer, and also the equivalent heat capacitance of the thermometer itself. So by calculating all these numbers from the measurement, then throughout this graph plot, you can actually determine what is TF and what is TI. So subtract TF from TI, so Q equals MC delta T, and then you get this thermal energy. And this thermal energy should be the same as the electrical work that's being done here. So electrical work, you can calculate that pretty easily because you know what is the current, what is the voltage. So multiply the voltage by the current here, and then multiply that by time it takes from point B to point C, and there you get electrical work. So here, we're going to be redoing the heat equivalence. So you know that the heat equivalence is the division between joules and calories. So be sure to calculate Q in calories and calculate W in joules. So divide these two numbers, and then you should have the conversion from joules to calorie to be 4.186. All right, okay, that would be all. So please enjoy the lab. Thank you.